is equal to 3, and here we have 4 polynomials of P2. For basis of P2 we only need 3 polynomials of P2, so we have to remove one polynomial so that the other 3 polynomial become basis for the P2, right? So just randomly we take first 3 polynomials, 1 plus x square minus 2 plus 2x square, 1 plus x square and minus 2 plus 2x square. Now from these 3 polynomials, first row is 1 1 0, then 0 0 1, then minus 2 0 2. From the third polynomial 1 1 0, 0 0 1, minus 2 0 2, that is equal to 1 into 0 minus 0, minus 1 into 0 plus 2, that is equal to minus 2, not equal to 0. Hence 1 plus x square minus 2 plus 2x square are linearly independent because the value of determinant is not equal to 0. Okay, the value of determinant is not equal to 0, so that's why you can say that these 3 polynomial are linearly independent. And using this theorem, using the previous theorem, these 3 polynomial become a basis for the subspace of P2 spanned by the given vectors. Okay, so here is the complete this question. Next question, question 3b, first part. Reduce S is equal to 1 0 0, 0 1 minus 1, 0 4 3 and 0 2 0 to obtain a basis for R3, right? Reduce this set of vectors to obtain the basis for R3. We know that dimension of R3 is equal to 3, and we have here 4 vectors of R3, right? To become a basis we only need 3 vectors. Okay, we only need 3 vectors. So for that we have to remove at least one vector. So just randomly remove the last vector. Take first 3 vectors and let S is equal to 1 0 0, S dash, this is S dash is equal to 1 0 0, 0 1 minus 1, 0 4 3. Try to check that these 3 vectors are linearly independent or not. For that we have to use this determinant 1 0 0, 0 1 minus 1 and 0 4 3. So this is 1 into 3 plus 4, that is 7, not equal to 0. Hence S is linearly independent. And here we use one theorem which states that if dimension of V is equal to n and S contains exactly n vectors, then S is a basis for V if S is linearly independent or S spans V, right? So we already proved that these 3 vectors are linearly independent. So these 3 vectors spans R3 automatically using this theorem, and that's why these 3 vectors are basis vector for R3. So this set S is a basis for this set S dash. This is our new set S dash, contains these 3 vectors, is basis for R3. Okay, so this question is complete. Next question, question number 3b, second part. Find the basis for the row space of A and column space of A for this matrix, and also verify the dimension theorem for matrices. Also verify the dimension theorem for matrices. What is the matrix? 1 4 5 2, first row, second row is 2 1 3 0, and the third row is minus 1 3 2 0, minus 1 3 2 0. Now first of all we have to convert this matrix into row echelon form, right? So that is our first target. We convert this matrix into row echelon form. We first reduce the matrix A into echelon form. This is our matrix A, 1 4 5 2, 2 1 3 0, minus 1 3 2 0. We multiply, this is our leading entry, we want 0 below that leading entry, so we want here 0. So that's why we multiply first row with minus 2 and add into the second row, and we multiply first row with 1 and add into the third row. So 1 4 5 2, first row is as it is. The second row, see, 2 minus 2 0, 1 minus 8 minus 7, 3 minus 10 minus 7, 0 minus 4 minus 4. Okay, then we multiply first row with 1 and add into the third row. So that is minus 1 plus 1 0, 4 plus 3 that is 7, 5 plus 2 that is 7, 2 plus 0 that is 2. Okay, now next process, we multiply second row with 1. Now this is our leading entry, below that leading entry now we have 0. In second row, this is our leading entry, minus 7. Below that leading entry we won't make 0. So that's why we multiply second row with 1 and add into the third row, right? So the second row, first and second row are as it is. The third row is 0 0 0 and minus 2. Just add this second and third row. Okay, so now this matrix is in row echelon form. To find basis for the row space, the non-zero rows form a basis for the row space of A. Basis for row space of A, that is non-zero rows from this matrix, the non-zero rows from this row echelon form matrix. So 1 4 5 2 0 minus 7 minus 7 minus 4 and 0 0 0 2. This 3 vector 1 4 5 2 0 minus 7 minus 7 4 0 0 0 minus 2. These 3 vectors are actually basis for the row space of A. Now we want to find the basis for the column space. Here is the method. In which column we have leading entry? First column, second column and fourth column. First column we have leading entry, second column we have leading entry, fourth column we have leading entry. Okay, so corresponding to first, second and fourth column, C, first, second and fourth column. Consider the first, second and fourth column from the our given matrix A, 1 2 minus 1 4 1 3 2 0 0. This 3 column vector 1 2 minus 1 4 1 3 2 0 0, this 3 column vector are actually the basis vector for the column space of A. Okay, so the leading entries are in the first, second and fourth column, hence the first, second and fourth column of A form a basis for column space of A. So the basis for column space of A, that is equal to 1 2 minus 1 4 1 3 and 2 0 0. Okay, now next question is actually we have to verify the dimension theorem, right? Now what is our rank of the matrix? Clearly you can see rank of a matrix is 3, because in row echelon form we have 3 non-zero vector, 3 non-zero row, right? So that's why rank of a matrix is 3. Okay, but to check dimension theorem we have to find nullity. To check dimension theorem we have to find nullity. For null space of A, we get these equations from the last matrix C. From the last matrix, x1 plus 4x2 plus 5x3 plus 2x4 is equal to 0. So here is the first equation, x1 plus 4x2 plus 5x3 plus 2x4 is 0. The second equations is from the second row, minus 7x2 minus 7x3 minus 4x4 is 0, right? And this third equation, minus 2x4 is equal to 0. So these 3 equations are coming from the row echelon form matrix, right? Now we know that x4 is already 0, and in third column we does not have any leading entry. So that's why we have to suppose x3 is equal to minus t. Okay, x3 is equal to minus t. Put x3 is equal to minus t and x4 is 0. you will get x2 is equal to t, and put all these values in this first equation, you will get x1 is equal to t. So basis for null space of A is 1 minus 1 1 minus 1 0, and nullity, clearly nullity is 1 because we have only one basis vector for null space. So clearly nullity of A is equal to 1, right? And rank is 3, nullity is 1, 3 plus 1 is 4, and exactly we have 4 number of column in the given matrix C. Okay, in this matrix A we have exactly 4 number of column. So clearly dimension theorems are satisfied, right? Rank is 3 because number of non-zero row in this row echelon form is 3. So rank is 3 and nullity we get 1. So 3 plus 1 is 4 and we have exactly 4 number of column. So that's why dimension theorem is satisfied. Okay, so here the complete the solution of this question. Next question. Question 3c. Show that S is equal to 1 2 1 minus 2, 0 minus 1 minus 1 0, 0 2 3 1, 0 0 minus 1 2 is a basis for set of 2 cross 2 matrix. We use the translation. Now again we want to check that the given this 4 matrices is basis for set of 2 cross 2 matrix or not. So we know that set of 2 cross dimension of set of 2 cross 2 matrix is equal to 4 clearly. Okay, because in general dimension of set of m cross n matrix, that is equal to m into n. Here we have set of 2 cross 2 matrices. So dimension of set of 2 cross 2 matrices, that is equal to 2 into 2, that is equal to 4. Okay, and here we have exactly 4 number of vectors, 4 number of set of 2 cross 2 matrices. So to prove that the given set is basis or not, just you only need to prove the given set is linearly independent. Okay, so let's try to check that the given set is linearly independent or not, set of vectors, right? So we use the translation ABCD matrix to ABCD row to convert S into the row space of A. Okay, so simply the first matrix we become a first row, right? The first matrix we become a first row of our matrix, new matrix 1 2 1 minus 2. So here is the 1 2 1 minus 2. See, then 0 minus 1 minus 1 0. So 0 minus 1 minus 1 0. Then 0 2 3 1. This is third row 0 2 3 1. This is 0 0 minus 1 2, and this is 0 0 minus 1 2, right? Okay. Now we multiply first row with 2 and add into the fourth row. So that's why the first, second and third row are as it is. Okay, 1 2 1 minus 2, 0 minus 1 minus 1 2 1 minus 2, 0 minus 1 minus 1 0, 0 2 3 1. The changes is in the fourth row, right? So we multiply first row with 2 and add into the fourth row. So the fourth row become minus 2 plus 2 0, 0 plus 2, that, right, that is here is 4, then 3 and minus 2, right? Okay, next process, we multiply second row with 2 and add into the third row, and we multiply third row with 4 and add into the fourth row. So 1 2 1 minus 2, the second row is as it is, 0 minus 1 minus 1 0, 0 0 1 1, 0 0 1 minus 2. In the next process we multiplied third row with minus 1 and add into the fourth row. So 1 2 1 minus 2, 0 minus 1 minus 1 0, 0 0 1 1, and then 0 0 0 minus 3. Okay, so you can see all the rows in the row echelon form of A are non-zero, right? Hence the set S is linearly independent. Okay, hence the set S is linearly independent. And you can say that the given set of vectors, hence we use this theorem which states that if dimension of V is equal to n and S contains exactly n vectors, then S is basis for V if S is linearly independent or S spans V. So we already proved that this set of vectors, this set of matrices is linearly independent. So definitely that this four matrices spans set of 2 cross 2 matrices, and hence S is a basis for V. V means set of 2 cross 2 matrices, right? So here is the complete this solution. Question 4a, first part, compute distance from F to G for F is equal to cos 2 pi x and G is equal to sin 2 pi x in vector space V, where V is a continuous function from 0 to 1, defined from 0 to 1, with inner product Fg. We use this definition, integration from 0 to 1 fx gx dx. This question asked in 2 marks. So clearly we know that the formula for distance from F to G, that is actually norm F minus G. Okay, distance from F to G, that is equal to norm F minus G, and that is equal to under root F minus G, under root F inner product with F minus G to F minus G, right? Now inner product with F minus G into F minus G, that is equal to, use this definition, inner product Fg, that is equal to integration 0 to 1 F into G. So inner product F minus G with F minus G, that can be written as integration from 0 to 1 F minus G into F minus G, that can be written as F minus G square into dx, that is equal to integration from 0 to 1 F square minus 2Fg plus G square, that is equal to integration 0 to 1 cos square 2 pi x minus 2 cos 2 pi x sin 2 pi x plus sin square 2 pi x. Okay, now cos square plus sin square is 1 minus 2 sin 2 pi x cos 2 pi x, that is equal to sin 4 pi x. 2 sin 2 pi x cos 2 pi x can be written as sin 4 pi x. Okay, because we know that 2 sin a cos a, that is equal to sin 2a. So we use that 2 sin theta cos theta is equal to sin 2 theta.